This is a review of Chapter 7 ideas, and Chapter 7 was dealing with momentum. I'm also going to toss in a couple of special examples and also throw in an example about angular momentum and how it relates to linear momentum. Okay, we have a car, or a truck, and a bulldozer that are heading towards each other. So what do we remember about this? Well, momentum by definition, we give it the letter P, is mass times velocity. And remember, velocity is a vector, so positives and negatives do matter. This one here is a negative 1.6 meters per second because it is going to the left or west, and this one is a positive 1.9. Now these two cars or two vehicles will collide together, and they can do two ways. Inelastically, if it does it inelastically, then they will stick together after the collision and have one common velocity afterwards. If it's elastic, the two will bounce off each other, and they will have two final velocities when they're done. So we do apply the theory or the concept that momentum is conserved. So we say momentum 1, and let's put a vector head on that, and also on this one here, must equal then momentum 2. So the sum of momentums before the collision must equal the momentum after the collision. So what equations do we derive from this? Well, inelastically looks like this. If we call this object 1 and this one object 2, we'll have mass 1 times velocity 1 plus mass 2 times velocity 2 equals, and we'll add the two masses together since they stick to each other, m1 plus m2 times some common velocity b when we're done. And then what's true about these collisions when they're inelastic? Well, kinetic energy 1 does not equal kinetic energy 2. So it's not conserved. Kinetic energy is not conserved in an inelastic collision. You'll find that in an elastic collision that kinetic energy 1 does equal kinetic energy 2. What we mean by that is the sum of all kinetic energy before the collision here does not equal the sum of the kinetic energy after the collision. For elastic, the sum of kinetic energy 1 does equal the sum of kinetic energy 2. It's conserved. And we're assuming a perfectly inelastic collision and a perfectly elastic. So what does the momentum equation look like for the bulldozer and the truck if they collide elastically? So I'll write that one down here. Change colors here to make sure it's obvious. So it will look like this. M1 VA plus M2 VB is equal to M1 VA sub 2 plus M2 VB sub 2. So what I mean by this is we have a mass times the beginning velocity for this vehicle, that would be the truck, plus mass of the bulldozer times its beginning velocity. And then afterwards we have two different final velocities. And that's how that works for an elastic collision. Now what about the forces and the impulse that occurs between these two when they collide with each other? Well, if we were to look at a graph of force and time before the collision and after the collision. So before the collision we have no force between them. And then we get a quick force that rises and falls as two vehicles collide. And then again we have no force afterwards. So impulse is going to be equal to force times time. So if I want the total impulse, then I can just simply take the area under this curve. It's just a triangle, so 1/2 base times height. And that will equal my impulse. Well, what does impulse equal? It also equals a change in momentum. We give impulse the letter I. Okay, so what does this look like then? So force times time is going to equal the mass of the individual object multiplied by its change in velocity. Okay, so in the previous example, you can calculate the impulse for the bulldozer separately from the truck. So you put the mass of the truck in there and subtract its final velocity from its beginning velocity. And likewise, do that for the bulldozer, but you can't do both together. But what's true in the situation, we do apply Newton's third law. A reaction is an equal and opposite reaction. So the impulse, and it's given the letter I, impulse of the truck must of course equal the impulse of the bulldozer. But of course equal and opposite. So one may be positive, the other one may be negative. And well, that's how we do it. Now, why does this equal change in momentum? Well, the units for momentum, of course being mass times velocity, is kilogram meter per second. So let's look at what force times time is. Well, force is a kilogram meter per second squared. If we multiply this by seconds, which is time, one of the seconds will cross off, and we are indeed left with kilogram meter per second, and we see that those units agree. So after I take the area underneath this curve, I could set that equal to the mass of the object, multiply by its change in velocity, and figure out the change in velocity or the final velocity for the object. And that's how we handle impulse and collisions for Chapter 6.